The next story has to do with if you are forming planets around stars, how do you actually detect them? And this is a topic that we've covered lots of times over the years here at 60 Minutes in Space. A lot of the detections are actually indirect, meaning you don't actually observe the planets themselves, but you observe the effect of the planet, like its gravity, indirectly. And the reason why you can't observe, or it's very difficult to observe planets directly, is what I like to call the searchlight or the firefly metaphor. And that is, if you have a bright searchlight that you're looking at, and you're trying to see a firefly or something really dim right next to it, that's almost impossible, just because the glare from that searchlight is going to overwhelm your visual senses. And this is the exact same problem that astronomers have when they're trying to look at planets around other stars. The parent star is so bright that the light that's thrown off by, or the light that's reflected by the planet is minuscule. And it's actually much, much worse than a searchlight versus a firefly. The visible light that an Earth-like planet reflects compared to the sun, it's about 10 billion times weaker than what you'd find for the light coming from the star. And so you'd have to, so the light, the glare from that star will just overwhelm the planet. Now there are workarounds. So here is an animation from the SOHO spacecraft, which looks at our sun. So, the sun is a very bright star, but it has an instrument called a coronagraph, and that's this thing here, which blocks out the light from the sun. So we can run this animation again. And what you see are a couple of comets. Those are those objects there. And then you can also see explosions from the surface of the sun that propels gas out into the solar atmosphere and into the solar wind. And so these features normally would be impossible to observe if you couldn't block the light from the sun. And so using this special instrument, the coronagraph, on this orbiting spacecraft, it's able to see these extremely faint features. And then similarly, here is another image showing another comet. This one doesn't plunge into the sun, but again, you can see the fact that once you've blocked the light of the sun, you're able to pull out these really faint objects. So this same principle can be applied to both telescopes on the ground as well as in space. And this particular this is an image taken with the Hubble Space Telescope of a star known as Fomalhaut. And here, Fomalhaut was observed over 2 different times, and they're able to inspect that patch right around the star. And so this, we're not seeing the star; it's been completely erased by that the coronagraph, but we can actually see a planet-like object orbiting this young star, which still has much of the protoplanetary disk in dust that's reflecting light. We're also able to do this on the ground. This is the Gemini Observatory. This is a set of observations from 2004 to 2008. So you can see the different planets showing up. And then here is yet another one, Beta Pictoris, where again they're using a ground telescope and using instrumentation to basically remove the glare from the star. And then, so this is one observation. The observation out here is from a different telescope that shows the extent of that protoplanetary disk, that disk of material that leads to the star and planet formation. So the the most recent work that I will be talking about comes from the European Southern Observatory. They have a bunch of telescopes down in Chile in South America, and they have a new instrument called SPHERE, which stands for Spectral Polarimetric High Contrast Exoplanet Research Instrument. And so this is another example of how astronomers like to string together a bunch of semi-relevant words and just to pull together, the right letters for their acronym. So this is a coronagraphic instrument, but it also takes advantage of the fact that you might notice the word polarimetry, and polarimetry has to do with how light, which is an electromagnetic wave, is oscillating, how the electric and magnetic fields are oscillating. And it turns out that when you look at reflected light, it tends to polarize the light. If you have experience with polarized sunglasses, you know that sunglasses can remove glare. And the reason why it's able to do that is that light from reflected surfaces tend to be polarized a certain way. And so the glasses can remove that. And so since the planets are reflecting light from the parent star, you can basically use this effect to basically just pinpoint the light from the planet as opposed to the star. And so what they were able to do was to look at 3 different stars, and each of these stars has the central light highly masked or removed from the coronagraph, and they're able to now pull out these features from the protoplanetary disk. So this is the disk that's feeding the gas and dust that's feeding the planet formation. Now, as far as what we're seeing here, you can see a lot of really interesting patterns. It looks like there are rings around this particular star, as well as arc-like features. There are also arc-like features here that may look incomplete. And then there's also this here, both these images, the plane of the disk is somewhat tilted, but here it looks like we're looking very close to right down the barrel of this protoplanetary disk. And instead of having just rings, we have this really interesting spiral structure. So how do we explain what we're seeing here? Well, again, we can turn to computer simulations and the theoretical work that astronomers have been doing for many decades. And so here is a computer simulation showing a planetary disk, a protoplanetary disk, and then a planetary core that's in orbit around it. And what happens is that as the planet pulls in gas from the disk, it excites these 2 spiral waves. So there's a wave that's going out as well as a wave that's going in. And this is just a matter of the fact that gravity is pulling the gas in towards the planet, and then the fact that things also orbit at different speeds. So stuff closer to the star orbit faster, and the gas, as you go further out, orbits slower and slower. And that leads to the spiral pattern that gets induced in the disk. And then here is another one where the simulation starts off with not just one, but a bunch of different planetary cores. And so you can see that you can instigate really complicated waves in the disk. And so the question is, is it possible for you to observe with telescopes waves like this? And then finally, here's a third simulation. Let's see if I can make this work. Where we're looking at again, top down in this part, but here we're looking at the side. And so here's that planet again. And what's going on is that as the material is getting pulled into the planet, it's also opening up a gap. So you can see a gap where the orbit of the planet is. And there's also a gap opening up both above as well as to the side of above and below, as well and to the side of the planet. And you can see this gap widening and clearing out as the planet continues to accrete gas and dust from the planetary disk. All right, so what are the interpretations of what we're seeing? In this case, this particular object, RxJ1615, the interpretation is that the rings and the arcs that we're seeing are due to multiple rings in the multiple gaps in the disk. And so here are a couple of models that appear in this particular paper by Yaste de Boer that just came out this past month. And their interpretation is that the ring material are of different heights in the disk, so they're not, and this is somewhat exaggerated, but you're basically seeing the outside versus the inside edges of this ring material and the obscuration. And of course, the material is only lit up by the star at the center. And so depending on your view geometry, you'll see different aspects of these rings around that star. And these gaps, presumably, are ones that have been opened up by planets that are forming inside that disk. And then as far as this particular star, HD 97048, the authors of this particular paper have a similar idea, where they're proposing that you have multiple rings, and again, the ring material have different scale heights, heights in the vertical direction, and we're seeing different edges of this ring material. And these gaps, again, are caused by forming planets that have cleared that disk material. All right, so that leaves us this spectacular object. And what's really wild is that we actually have two Sparrow Arms. So you have one arm here, and you have one arm there, which suggests, if we believe some of the computer simulations that we've seen, that there might be two planets that are forming in this disk. What's also really interesting is that if you look, there also appear to be shadow bands. So notice that the rings aren't perfectly consistent in brightness, but there's a drop in brightness here and here, and here and here, and here, and maybe here as well. And you can actually draw lines connecting up these darker regions. And so they suggest that there might be material that's obscuring the central star. And so the star is lighting up the material all around here, except for right about here, here, and here. So what the authors of this paper did was to do their own theoretical work to show how you can actually, depending on, you can actually have two different scenarios. So you can actually have planets both inside the Sparrow, and then and they also have another model where the planets are located outside the Sparrow. So here in this case, these two purple crosses and the two purple dashed lines show the Sparrow patterns that are brought about by two planets located here and here. And then the other model, you can also have planets located inside the Sparrow pattern, which can explain most of the Sparrow, but they don't quite explain the gap here. So it seems like a model where the planets are located further out beyond the visible Sparrow does a better job of explaining what we see or what we observe. And then finally, to try and explain the so-called shadow bands here, what the authors involved in this work further did was they actually took this image, taken at different wavelengths, and they unwrapped it. And so this is what we're seeing here, where each of these bands corresponds to the individual bands here. So they basically took that circular image, pulled it apart to try and analyze it, and then they built a model where they assumed that there were actually multiple disks involved. So you didn't have just a single disk, but you had an inner disk that was tilted with respect to the outer disk. And there's a connective zone, this red region, that connects the two disks. And it's the fact that you have shadowing from this warped disk that connects the two disks that leads to these shadows that we see. And so they're able to, again, create simulations that do a relatively good job of recreating the shadow bands. So here are the two bands that are from their simulation, where they're simulating the light that's being scattered, that's coming from the star, and it's scattered by the dust particles that are embedded in these disks. And so they do a decent job of, at least qualitatively, explaining the bands that they see. All right, so this is all pretty exciting stuff, and as our telescopes and instrumentation continues to improve, you can expect that we'll be able to get more and more information about the planetary and stellar formation process. Because what's really exciting about this is that, we are, a lot of the stuff we can't actually directly observe. I mean, it's hard to observe the planets that are in the orbits around these young protostars, but we can observe the effects of the planets on the disk. And we can observe, indirectly, things like disk warps that cause these shadow bands. So as our observations improve, we'll continue to map and to understand things at much smaller scales, scales smaller than what's visible in our views with our telescopes. All right.